I made a worksheet you can fill out as you watch this video, plus practice problems for this unit, and AP Calculus practice tests to help you get ready for the AP test. So click the link in the description to check those out. In Units 2 and 3, we learned about derivatives and the different rules that we use to calculate them, and we're going to apply all of that here in Unit 4, which is really all about how to solve real-world problems using derivatives. The hardest part of this unit is definitely going to be topics 4.4 and 4.5, which are all about related rates problems. The good news is that related rates problems, even though they can be confusing, do get significantly easier when we practice a lot of them. So that's definitely something you'll want to dig into to get ready for the AP test. The big takeaway from topic 4.1 is really just about being able to understand the relationship between the original function, its derivative, and its second derivative. So let's say, for instance, that we have this graph, and let's say that it models a person's height over their lifetime. So we'll call this function h of t to indicate that its height at time t, where t is given by the number of years that the person has lived. So graphed on an axis like this, we'll say that this is the t-axis, time, and this is the height axis, h. So the person is born here, and as they go through their childhood, their height gradually increases, and then maybe when they get close to adolescence, they hit this growth spurt, and their height shoots up to kind of the point where it's going to remain for the majority of their life. And so they live out their life at this height, and then maybe when they're very old, maybe they lose just a little bit of height. Some people get just a little bit shorter as they get into very old age. So maybe this curve models the person's height over time. All we need to be able to understand here is what h of t can tell us, what the first derivative, h prime of t, can tell us, and what the second derivative, h double prime of t, can tell us. So we want to first think about the original function h of t. So we have this curve here. Well, if I take any value of t, so let's say I may be interested in this point right here, maybe this is t equals 70 when they're 70 years old. So what I see is that if I just come up here from 70 to the point where I meet the function, right here, what I'm going to get is a particular height at time t equals 70 years. So my height is going to be right about here. So this h of t function, the original function, is just giving me height at a particular moment in time. So height at time t. I can plug in age 70, I can plug in age 13, age 4, age 35 into that original function, and I'm going to get height at that particular time. The derivative function, however, gives us the rate of change of the original function. It gives us the slope of the original function. If I think about slope, I think about the tangent line. So basically, this is just how fast is height changing. Well, we can see if we look at this graph here, the slope is steepest maybe in this interval right here. That's adolescence maybe, where they hit this growth spurt. So the slope of the function is steepest. If we sketch a tangent line, we can see here, maybe this is our point of tangency, and then if we sketch a line through that, we see that the slope looks something like that. It's very steep, versus the slope at this point right here is basically flat. Height isn't changing at all necessarily. The slope of the tangent line is flat there. So we could describe this many different ways, but we could think of the derivative function as modeling the rate of change of height, or we could call that, like we said, the slope. And so depending on whether or not the derivative was positive or negative or zero, if it's positive, we know that height is increasing because the slope is positive. If it's zero, we know that height is staying the same. And if it's negative, like it would be over here, the slope is negative, then we know the person that they're getting shorter. And then of course the second derivative, which is the derivative of the first derivative, that's going to give us, you can think about it as rate of change of the rate of change. It tells us how fast the slope is increasing or decreasing. In the context of motion, we think about that as acceleration, but in a context like this of height, we could think about this as modeling whether or not the growth rate is increasing or decreasing. For example, here on this interval, it looks like the growth rate is increasing. They're starting to grow faster and faster as they get here toward adolescence. But on this interval right here, we can see that the growth rate is starting to taper off. It's starting to slow down. The slope is decreasing here versus here the slope is increasing as we move. So over here, the second derivative would be positive, but over here it would be negative because the growth rate is speeding up versus slowing down. So the goal here is just to be able to understand that relationship between the original function, first derivative, and second derivative. And we want to be able to think about this relationship in all different kinds of contexts. So whether we're modeling height, or if we're modeling the size of an object that's growing or shrinking, or we're modeling a population or temperature, any kind of value that's changing over time, we want to be able to understand that that first derivative represents the rate of change of the original function, and that that second derivative represents the rate of change of that first derivative. The most common type of relationship that we look at between the original function, the first derivative, and the second derivative is the relationship between position, velocity, and acceleration. And so we think about these as motion problems, and specifically we look a lot at straight line motion problems, but we'll talk about that in a second. So position we like to think of as the original function, and oftentimes we'll indicate that with x of t. We'll call the function x of t. Velocity is the derivative of that. So velocity is always the derivative of position, so it's x prime of t, and we write that as v of t as well to indicate velocity. And then acceleration is the first derivative of velocity, and it's the second derivative of position. So we'll write that as either x double prime of t, as v prime of t, the derivative of velocity, or we'll call it acceleration, a of t. So you want to be familiar with these and the fact that taking the derivative of position gives velocity and taking the derivative of velocity gives acceleration. Oftentimes we'll look at straight line motion problems or rectilinear motion problems, and you'll be told, for instance, that a particle is moving along a straight line or from east to west or along the x-axis, but the point is along some horizontal line like this. And so if you imagine you have a particle here and it's moving along this line, it might move to the right sometimes, then back to the left, then back to the right, but it's moving perfectly horizontally. We want to be able to think about that in terms of position, velocity, and acceleration. So if the particle is moving to the right in this direction, then velocity is going to be a positive value. If the particle has moved to the left, then velocity is going to be a negative value. We also want to know that when velocity and acceleration have the same sign, that the particle is speeding up, but when they have different signs, that the particle is slowing down. We also want to be able to say that the absolute value or the magnitude of velocity is going to be equal to the speed of the particle. So if we want to find speed of the particle, we just take the absolute value of velocity. Obviously, when we look at a problem like this one, we want to be able to distinguish between distance traveled and displacement. So depending on how the particle moves, maybe it starts here and it moves off to the right, and then it moves back to the left, and then it moves back to the right, and then eventually just continues on to the right for some time. We could find that total distance traveled. That's different than the displacement, which is just the difference between its starting and ending positions. So if the particle starts here and it goes something like this, and then it moves around and goes something like this to here, and then it comes around back this way, and it moves like this, and eventually ends up at this ending point right here. This whole distance, this whole snaking distance is the total distance traveled, but the displacement is just the difference between the starting and ending point right here. So in general, given a position function, something like this, we've been given this position function here, the most critical thing is first to be able to find velocity, which we find, as you know, by just taking the derivative, so we get 6t plus 6, and then to find acceleration by taking the derivative of velocity, so we can see that that's 6. that gives us position, velocity, and acceleration functions just by taking derivatives. Then we can answer all kinds of questions with these three functions in hand. For instance, another question we can answer is to find average velocity over a particular interval. So if we want to find, let's say, average velocity over the interval, we'll say 0 to 9, so between t equals 0 and t equals 9, then we just use that difference quotient formula, and we say t equals 9 and t equals 0, and then we divide by 9 minus 0. And so the result there is we plug 9 into the velocity function. We get 6 times 9 is 54. 54 plus 6 is 60. So we get 60 minus plugging 0 into the velocity function gives 6. So we get 6 here, and then 9. So we get 54 over 9, or 6. So average velocity between t equals 0 and t equals 9 is 6. Or if we wanted to find average acceleration, so let's say acceleration over the same interval between t equals 0 and t equals 9, we would say this, we would set up this difference quotient value, 9 minus 0, and we would get here, when we plug 9 and 0 into the acceleration function, we just get 6 either way. So we get 6 divided by 9, well, we're just going to get 0 in the numerator. So average acceleration between t equals 0 and t equals 9 is 0. We want also to be able to think about units for each of these values. So the original position function tells us where the particle or the object is located. So if we find a value for position, the units will be in terms of whatever distance we're measuring in. So let's say that we're calling t time after t seconds, and we're giving position in terms of miles. So we're talking about miles per second. Well, the position function is going to return something in terms of miles. The velocity function is going to return something in terms of miles per second. And the acceleration function is going to return something in terms of miles per second squared. And then average velocity and average acceleration, average velocity is going to be miles per second as well, whereas average acceleration matches acceleration here, miles per second squared. So just remember, with these kinds of problems, if you're starting with a position function, you take the derivative to get velocity, you take the derivative to get acceleration. Always start with those three functions. Once you have those in place, then you can start tackling all of the questions that come along with problems like these in terms of where is the particle speeding up or slowing down, or to find the speed as the magnitude of velocity, or to find average velocity or average acceleration, all these different values. But starting with these three functions, getting those down first, is always the place you want to start. In 4.3, we really just want to think about rates of change in general. So in 4.2, we talked about motion, we talked about position, velocity, and acceleration. But as you know, there are rates of change all around us in every industry and every aspect of life. Earlier on in the video, we looked at height and how height could change over time, and how if we were given a function h of t that models height, then finding its derivative, h prime of t, would give us the rate of change of the height to tell us if we are growing or if we're shrinking. And then h double prime of t, the second derivative of height, would tell us whether or not that rate of change is itself increasing or decreasing. So there's all these different contexts. We can talk about rates of change in terms of the population. If we have a population function, p of t, and then the derivative tells us if the population is growing or if it's declining. You can look at someone's weight. If they're fluctuating in weight, they're gaining weight, they're losing weight, and the original function would model weight. So after a certain amount of time, t, for example, if someone's trying to lose weight and you say t is the number of weeks since they started, at t equals 3, the original function would give their weight in the third week. But the derivative function would tell you whether or not they're gaining or losing weight. So if we plugged in t equals 3, the derivative function w prime of t would tell us if they're gaining weight at that point or losing weight at that point. And the second derivative function would tell us whether they're starting to gain or lose weight faster or slower. We could talk about this in terms of businesses. So For example, the cost of producing a certain good. Maybe we're talking about a sunglasses company and we're talking about the cost of producing a certain number of sunglasses. So let's say the cost of producing S sunglasses. That original function, if we plugged in S equals 100, C of S would give us the cost that it takes in order to build those 100 pairs of sunglasses. The derivative function, C prime of S, would tell us whether or not at S equals 100, cost is increasing or decreasing. And we can do this with area and volume functions as well. So for instance, if we want to look at the area of a circle, area equals pi r squared, and we want to, let's say, take the derivative of the area function with respect to its radius, we would differentiate with respect to r, and we would get dA over dr equals 2 pi r, and this would give us the rate of change of the area of the circle with respect to the radius, or in terms of the value of the radius. If we had an equation for the area of a triangle, the area of a triangle is 1/2 times the base times the height, and we want to differentiate with respect to the base b, we'd say dA dB is equal to, in this case we hold h as a constant, and so we would just get 1/2 h because the derivative of b is 1. The whole idea here is that you want to be able to think about rates of change in different contexts. There's literally an infinite number of different examples you could come up with for rates of change in the world around you, and you just want to be able to model in your head or reason through in your head what that original function represents, what its derivative function is telling you, and what that second derivative function is telling you. Calculate the first and second derivatives, and then be able to answer questions using those functions and actually interpret what those values are telling you. In the next topic, 4.5, we'll really dig more into how to solve related rates problems. But in this topic, we really just want to introduce the concept and go through sort of the process of what a related rates problem looks like. So in general, these are the steps we're going to follow. When we're given a related rates problem, we want to first draw a picture, then we want to write an equation that relates the values that we have been given, including the unknown value that we want to find. Then we want to be able to differentiate that equation using chain rule. Then we're going to plug in all the values we've been given and solve for the unknown that we're looking for. And then we need to be able to interpret our result. So we need to understand what our result means in context. So just to sort of walk through these steps, let's look at an example. In this example, we've been told that a 1 meter long shovel is leaning against a fence, sliding down it at 0.25 meters per second. And we've been asked, at what rate is the shovel sliding along the ground away from the fence when the top of the shovel is 0.5 meters off the ground? So there's a lot going on there, but really we just need to follow our process, picking out the pieces of information from the problem that we need, and we'll be able to walk straight through it. So the first thing we want to do is draw a picture. And we have a shovel leaning against a fence. So let's just say here that this is the fence, this is the ground, and then we'll call this here the shovel. So the shovel is leaning against the fence like this. And so right away, we see that we have a right triangle. We know that this is a right angle here between the fence and the ground. And we can go ahead and call this the fence. We'll call this the ground, and we'll say that this up here is the shovel, just to help remind us. So that's it for drawing a picture. Now we need to write an equation. Well, usually when we have a right triangle, the equation that we use, because it's the equation that relates the three sides of the triangle, is going to be the Pythagorean theorem, a squared plus b squared equals c squared. In our case, let's call the ground side A, the fence side B, and the shovel side C, because C is always the hypotenuse. So that's going to be the equation that we're going to start to work from. And then we want to differentiate with chain rule. And this goes back to treating each of the variables as a function with respect to time. So when we differentiate each variable, we do it like we did with implicit differentiation. So the derivative of a squared is 2a, but then we have to multiply by dA over dt. The derivative of b squared is 2b, but then we multiply by dB over dt. And the derivative of c squared is 2c, but then we multiply by dc dt. So every variable in the equation, we differentiate it, but then we multiply by that rate of change with respect to t of that variable. So that's our step for differentiation. Then we go ahead and plug in everything we know and solve for the value that we want. So what do we know from the problem? First of all, we know that the shovel has a length of 1 meter. Well, the length of the shovel is given by c. So over here, we can say 2 times 1. And then what about dc dt? Well, this is the rate of change of c with respect to time. But the length of the shovel doesn't change. It doesn't matter at what point in the sliding process we're at, the length of the shovel stays the same. So the rate of change of a constant is 0. If it stays the same, it's not changing. So that rate of change is 0. So we plugged in everything on the right-hand side. And then on the left over here, we're told in the problem that the shovel is sliding along the ground away from the fence. So as it does that, as it slides down, what we know is that the top here is going to slide down. So the top is coming this way, which means that the length of B is going to be decreasing over time. The bottom of the shovel is sliding away from the fence along the ground. So the bottom is sliding this way, and the length of A is going to be increasing. It's going to be getting larger. We know from the problem that the shovel is sliding down the fence at 0.25 meters per second. So that means that the top here is sliding down at 0.25 meters per second. So B is getting smaller at a rate of 0.25 meters per second. Well, the rate of change of B is dB over dt. So we can go ahead and plug in for that and say negative 0.25. And we use a negative value because B is shrinking. The length of side B is getting smaller. And then we've been asked to find a value when the shovel is 0.5 meters off the ground. So that's saying that we're interested in the point in time at which this length right here is 0.5. So when B is 0.5, so we can plug 0.5 in for B. We keep our 2 here. All that's left now, notice we plugged in for everything. All that's left to plug in for is A and dA over dt. Well, what have we been asked for? We've been asked at what rate is the shovel sliding along the ground? Well, that is dA over dt. That's the rate of change of A, how fast A here is increasing. That's going to be our unknown. That's the value we want to find. It's the value we want to leave in the equation. But we need to get rid of this A here. So how do we find A? Well, that's where we go back to our Pythagorean theorem. We know here that side B is 0.5. We know that side C is 1 because the shovel has length 1 meter. So we can use the Pythagorean theorem to solve for the value of A. So we say A squared plus, instead of B squared, we say 0.5 squared is equal to C squared, or 1 squared. So we get A squared plus 0.25 equals 1, or A squared equals 0.75. If we write 0.75 as 3 over 4, and we take the square root of both sides, then we get A is equal to square root 3 over 2. So now we have a value for A, and we say 2 times root 3 over 2. That's our value for A. And then we have dA over dt. And now we've got everything plugged into the equation. So notice how we were able to plug everything in, but we got stuck with A and dA over dt. We figured out that dA over dt was the value we needed to find, which told us that we had to go back somewhere, somehow, and figure out a value for A, because we have to plug in for everything other than the single value we're trying to solve for. So we knew we had to go back and find some way to find A. So we looked for information in the problem to realize that we could find A, solve for A, using the Pythagorean theorem. And so then, of course, you would simply solve this equation. So over here on the right, we're going to get 0. Here, 2 times 0.5 is 1. So we end up here with negative 0.25. Over here on the left, we get 2 in the numerator to cancel with 2 in the denominator. So if we add this 0.25 to both sides, we end up with root 3 dA over dt equals 0.25, or we could rewrite this as 1/4. And then if we divide both sides by root 3, we get dA over dt is equal to 1 over 4 root 3. But then we want to rationalize the denominator by multiplying both the numerator and the denominator by the root. And we say dA over dt is root 3 over 12, because root 3 times root 3 is 3 times 4 is 12. So we say that the rate of change of A is root 3 over 12. And so our last step then is to interpret. And what does this mean? Well, the fact that the value is positive means that the length of A is increasing, and that matches what we know about this problem. The shovel is sliding away from the fence, which means the length of side A is going to be increasing. So the fact that this is positive, that checks out. And it just tells us that the shovel is sliding away from the fence along the ground at a rate of root 3 over 12 meters per second. And so that's how we interpret that answer. So the goal in 4.4 was to really focus on the idea behind related rates problems and what they are. But in 4.5, we really just want to focus on problem solving. So we're going to look at another problem, and in this one, we have a plane flying horizontally at 360 miles per hour, 5 miles above the ground, when it passes overhead. How fast is the distance between you and the plane increasing? 40 seconds later. So we remember here our problem-solving process that we go through, but of course our first goal is to draw a picture of the situation. So we're standing on the ground, so let's say that this is us here, and we're standing at ground level, so let's just say this is ground level here. The plane passes directly above us, so let's say that directly above us is right here. We know that we have 5 miles between us and the plane, so this is 5 miles overhead, and the plane is flying horizontally. So let's say it's flying this way, so the plane is going to be over here later on, and so then we could sketch in the distance between us and the plane as this distance right here. And so right away when we sketch the problem, we see that we have a right triangle. And so we're going to go back to the Pythagorean theorem. So we have a picture. We're going to write an equation, and that equation is going to be, as you know, a squared plus b squared equals c squared. We'll call the hypotenuse, the distance between us and the plane, c. We'll call this leg a, and we'll call this leg b. And that's going to be our equation. So we'll write the equation there, and then of course we'll differentiate it. So when we differentiate, let's bring this up here. We know we're going to get 2a and then dA over dt plus 2b dB over dt, and then 2c dc over dt. And now we want to start figuring out which values we have. Well, we know that the plane is flying perfectly horizontally and that it's 5 miles above the ground, so A is always going to be 5. So A will always be 5. And the rate of change of A, because A is constant, the rate of change is 0. So dA over dt is going to be 0. In order to find B, we're going to have to use the fact that 40 seconds have passed and the plane's been flying for 40 seconds. Notice also that the plane's traveling at 360 miles per hour, but we've been asked about 40 seconds later. So we have hours and seconds. Those units don't match. We need to make them match. So let's convert 40 seconds into hours. The way that we do that is we say 40 seconds, we multiply it by 1 minute in 60 seconds, and then we say that there's 1 hour in 60 minutes. And when we do that, we get units of minutes to cancel, we get units of seconds to cancel, leaving us with just hours. And so we get 40 over 3,600, so 40 over 3,600, which is equal to 4 over 360, which is equal to 1 over 90 hours. So after 1/90th of an hour, how far has the plane traveled? Well, it travels 360 miles in an hour, so we could multiply this by 360 miles in 1 hour. When we do that, we get our units of hours to cancel, and we're left with 360 miles, we'll say this is miles here, divided by 90, or 4 miles. So in 40 seconds, the plane's traveled 4 miles, which means our value for b at the moment we're interested in is 4. So we can say plus 2 times 4. We know the rate of change of b is 360 because the plane's traveling at 360 miles per hour. So the length of b is increasing by 360 miles every hour. So that's a positive 360 because that distance b is increasing. And then on the right-hand side, in order to find c, we'll use the Pythagorean theorem. We know that a is 5 and b is 4. We need to find c. So 5 squared gives us 25. 4 squared gives us 16. So we end up with c squared equals 41, or c equals root 41. And so over here, we say root 41, and dc over dt is the value that we're trying to solve for. How fast is the distance between you and the plane increasing? That's the rate of change of c. dc over dt is the rate of change of c, so we leave dc over dt. So now we have differentiated with chain rule, and we've plugged in to our equation we just need to solve. This whole term goes to 0. When we divide both sides by 2, we'll get the 2's to cancel here, and we'll be left with 4 times 360 is 1440. So 1440, and then divided by root 41 is equal to dc over dt. If we calculate 1440 divided by root 41 as a decimal, we see that it's approximately equal to 224.9, or about 225. So that tells us that the distance between us and the plane is increasing at a rate of about 225 miles, exactly 40 seconds after the plane passes us overhead. That's how we interpret that result. Because the result is positive, we know that the distance between us and the plane is increasing, which makes sense since the plane is flying away from us. So again, with these related rates problems, you want to follow this set of steps, and if you ever run into a snag where you know you need to plug in for a value that you don't have already, you need to go back to the problem, back to the diagram, figure out a way to solve for it, and just be careful with your positive and negative signs, depending on whether a value is increasing or decreasing. And remember also that, especially with related rates problems, they get easier with practice. So definitely get as many of these under your belt as you can. .6 is all about approximating the value of a curve using a local linearity or linearization, which you can really just think about as the tangent line approximation. Remember that the point-slope form of the equation of a line is given by y minus y1 equals m times x minus x1. And really, there's just 3 pieces of interesting information here. M, which is the slope of the line, and then x1 and y1, which together make up a point that the line passes through. So really all we want to be able to take away from here is that we want to be able to start with some function. So let's say that we start here with f of x, and we want to be able to find a tangent line at a point. And remember, to do that, we need to be able to find those 3 pieces of information that we talked about. So we need to be able to find here m, x1, and y1. So let's say that we've been asked to find the tangent line at x equals 1. So in order to do that, first of all, we plug x equals 1 into the original function, because x equals 1 is what we're going to put in for x sub 1, and then y sub 1 is going to be the value of y that corresponds to x equals 1. So we simply say f of 1 is equal to, and we plug in here, so we get 1 squared minus 6 times 1 plus 1, and the value there is going to be 4 minus 6 plus 1, which is a negative 1. So that tells us that y is equal to negative 1 when x is equal to 1. These are our values x sub 1 and y sub 1. Then to find the slope m, we just take the derivative of the function and evaluate it at x equals 1. So our derivative f prime of x is going to be, we'll apply power rule here to the polynomial function, so we'll get 8x minus 6 for the derivative, and then evaluating the derivative at 1 gives 8 times 1 is 8, 8 minus 6 is 2, so we get a value there for 2. So this is m, this is x sub 1, and this is y sub 1. So to find our tangent line equation, we just plug in. So we say y minus y1 is negative 1, so negative 1 equal to m, which is 2, times x minus x sub 1 which is 1. And then we simplify. So y plus 1 is equal to 2 times x minus 1. This is our tangent line equation, and keep in mind that we can write this different ways. So we can solve for y by subtracting 1 from both sides and rewrite this as y equals 2 times quantity x minus 1 minus 1. We can also expand this out here to write this as 2x minus 2 minus 1, or y equals 2x minus 3. So just keep in mind that if on the AP test you're looking for a tangent line equation, you might see it given in this form, you might see it given in this form, or you might see it given in this form. They're all equivalent, so you need to be able to convert back and forth between those. Once you have your tangent line equation, so once you can get to this point, the only other thing we want to be able to do is use this equation, which is the tangent line equation or the linearization. We want to be able to use this equation to estimate the value of the function at a particular point. Remember, this is the tangent line equation that intersects the graph of f of x here at x equals 1, which means that this tangent line equation should give us a pretty good estimate of the value of the function around x equals 1. So for example, we could maybe use the tangent line equation to estimate the value of the function at 1.1. So in order to do that, we would simply plug 1.1 into this tangent line equation. So if we do that up here, what we would get is y is equal to 2 times 1.1 minus 3. That gives us 2.2 minus 3, or negative 0.8. So the approximate value of this function f of x at 1.1 is negative 0.8. And you might be saying, well, why wouldn't we just plug 1.1 into the function itself to get the actual value, the exact value? Well, sometimes you're going to be able to do that. Like here, we could do that. But sometimes the function will be undefined at 1.1. It'll have some kind of discontinuity there. We won't be able to find the value for some reason. And in that case, a tangent line approximation or linearization can work well to give you an estimate. The only other thing we want to be able to know how to do is to determine whether or not this estimate is an overestimate or an underestimate. If we can evaluate the original function at the point at which we're estimating, so if we can evaluate f of x at 1.1, we can go ahead and plug it in there, see what the actual value is, and then compare that actual value to our estimate right here to see which one is greater. If the actual value is larger than the estimate, then the estimate is an underestimate. But if the actual value is smaller than the estimate, then the estimate is an overestimate. We can also see that from the graph. So let's say, for example, we're given these two curves here. And let's say that for this first curve, we found the tangent line approximation at this point right here. And the tangent line looked something like this. So let's say we drew it through here and it looked something like that. Well, if we now use this tangent line approximation to estimate the value of the function, let's say at this point right here, we can see the value on the tangent line is going to be here, but the actual value is going to be up here. So the tangent line approximation is going to give an underestimate. But if we have a graph like this one, and let's say we find the tangent line approximation right here, and our tangent line looks something, let's say, like this, and then we use that tangent line approximation to estimate the function at this point, we can see that the line is going to give us this value here versus the actual value of the function is here. So the tangent line approximation is going to give us an overestimate in this case. What this should show you too is that if on the interval between the point of tangency and the value that we're estimating, so if on this interval the curve is concave down, then the tangent line approximation is going to be an overestimate. But if on the interval instead, the curve is concave up, this curve here, this graph is concave up, then the tangent line approximation is going to give you an underestimate. So that's one way to know as well, looking at the concavity of the function between the point of tangency and the point of estimation. That can also tell you whether or not you're going to have an overestimate or an underestimate. .7 is about using L'Hopital's rule to find the limits of indeterminate forms. And you're going to get multiple L'Hopital's rule problems on the AP test, so we really want to make sure that we know how to do this. The first thing we have to remember is that L'Hopital's rule is different than quotient rule. When you use quotient rule, you take the derivative of the ratio. Remember, a ratio is a fraction. So when you apply quotient rule, you're simply taking the derivative of the fraction. But when you apply L'Hopital's rule, you're taking the ratio of the derivatives. You're taking the derivatives of the numerator and denominator separately, and then taking their ratio, putting those into a fraction. So just remember that as a way to distinguish between the two. And then the first thing that we always have to do when we want to use L'Hopital's rule is we must show that we find an indeterminate form when we use substitution before applying the rule. So for instance, in this problem here, the limit as x goes to 0 of e to the x minus cosine x divided by x, what we need to do first is use substitution by plugging in x equals 0 to prove that we get a form 0 over 0 or infinity over infinity, because we're not allowed to apply L'Hopital's rule unless we first find one of these indeterminate forms. So in this problem, we would plug in x equals 0, and we would get e to the 0 minus cosine of 0 is going to be equal to e to the 0 is 1, cosine of 0 is 1, so we get 1 minus 1 or 0. And then in the denominator, when we plug in x equals 0, we get 0 in the denominator. So we end up with 0 over 0 as the indeterminate form. We have to be careful here because we can't say, it's not technically correct to say, that this is equal to 0 over 0. We don't ever want to write it that way because 0 over 0 is a form. It's not a value. So we can't say the limit is equal to 0 over 0. This doesn't make sense. Or we wouldn't want to say that it's equal to infinity over infinity. You don't want to set this equal to an indeterminate form. What you want to do instead is, off to the side like we did here, find the value of the numerator and denominator separately, or you can write it this way: the limit as x approaches 0 of the numerator, e to the x minus cosine of x, is equal to 0, and then alongside that, the limit as x goes to 0 of the denominator, x, is equal to 0. And because we have 0 and 0 here for both, we say that this leads to an indeterminate form, something like that. Once we've shown that we have an indeterminate form when we apply substitution, then we can apply L'Hopital's rule. And to do that, we leave the limit notation as is, and then we replace the numerator with its derivative. So the derivative of e to the x is still e to the x, and the derivative of cosine of x is negative sine of x. So we get minus negative sine of x or plus sine of x. And then in the denominator, we replace the denominator with its own derivative. The derivative of x is 1. So we've applied L'Hopital's rule once. Now we want to go ahead and simplify. We don't need to write a denominator of 1. So we'll simplify this to e to the x plus sine of x. Now, after every application of L'Hopital's rule, you want to try substitution again. So let's try substitution. This time we'll say we get e to the 0 plus sine of 0. E to the 0 is 1, and sine of 0 is 0. So we get 1 plus 0 is equal to 1. And we get a real number answer, not an indeterminate form. So that's going to be our answer. This is the value of the original limit. If you find an indeterminate form again after using substitution, you just want to apply L'Hopital's rule a second time. After you apply it a second time, simplify that value as much as possible, that function as much as possible, and then try substitution again. And you can keep doing this over and over until you eventually get to a real number answer. Okay, so that's it for Unit 4. You really want to make sure that you know how to find the velocity and acceleration function given the position function and answer all kinds of questions about those three functions. You also want to make sure that you know how to solve lots of different kinds of related rates problems. And remember that these get a lot easier with practice, so the more of these you can practice, the better. You want to make sure you know how to use a linearization or a tangent line approximation to estimate the value of a function, and you need to be able to say whether or not that estimate is an over or an underestimate. And then lastly, you want to be able to use L'Hopital's rule to evaluate the limit of an indeterminate form. And you need to be able to show first with substitution that you have an indeterminate form, and then apply L'Hopital's rule 1 or 2 times or however many times it takes in order to find the real number value of the limit. Once you're good to go on Unit 4, make sure to come back and move on to Unit 5, where we'll dig into optimization with derivatives.